So before I move on to our second example, it dawned on me after I stopped recording that the one thing I didn't do is go back and say, can we indeed ignore the hydronium concentration from the previous example? And what did we come up with? We came up with the hydronium concentration of X, there we go, is this 1.6 times 10 to the negative 3. And autoionization of water, remember, is this 10 to the negative 7. There we go. So it would be equal for both. So 10 to the negative 7 is many orders of magnitude smaller than what we came up with for our hydronium concentration. So that tells me that it's going to be insignificant. I mean, so if we added it together, that'd be like 0.1, 2, 3, 4, 5, 6, 7. And then plus 0.1216. So even if we included it, that small little, the 0.017 or the 0.01 part isn't even going to show up in our sig figs. So that tells me that we can ignore the kW part. All right, now let's go on to our next example. I want you to pause the video, look at the information you've been given, and set that up as best you can, as complete as you can, and then come on back. Okay, so let's see. I look at this, I'm like, okay, I've been given a Ka, and I've been given this thing aniline, and so I'm going to treat this as an acid. So I'm going to have this C6H5 NH2 aqueous plus water. And then I'm going to come over here and I'll be like, okay. She told us that the hydrogen won't break from a carbon. So this has got to go to something like C6H5 NH. And then I'm like, whoa, is that? So this would be, I'm calling this a weak acid. It means I'd be calling this a weak base. And then plus H3O plus. I don't know. Does this feel like this would be an acid or a conjugate of this? What would I be breaking? Here's the structure. So I'm saying that I would break a hydrogen-nitrogen bond from here. When there's kind of like these extra electrons hanging out. So it kind of feels water-ish. But doesn't it feel a little bit awkward? What was one of the rules that we came up with? What did we say about nitrogen and its lone pair? I feel like we said what's going to happen is if I have a hydrogen that gets near this lone pair, it's going to pop on here, and it's going to give me this structure. I'm not going to make it as pretty because I can't. It looks something like this, and that's how we shorthand these benzene rings. 2 nitrogen. I'm going to get something like this. And that makes more sense. I've now added this on. So I've lost some electron density. So that means that this thing is going to be like a plus charge. That makes more sense to me. But then I come back here and I'm like, but I have a Ka. And maybe the hint of the Kb expression might have told you that this is not how this was going to play out. So let's write this correctly. This is going to be a Kb. And how can I relate Kb to Ka? That's the next question. Let's see. What do we know? We have the autoionization of water equals the concentration of OH minus times the concentration of H3O plus. I don't know why my brain just suddenly didn't want to do that. But remember a few sections back, the other way we looked at that is we could write these concentrations in terms of their Ks. Remember, that's how we came up with a whole new K. So I can go KW is then my KB times my KA. Because remember, if I wrote this out, I could do like a net water reaction for both my hydroxide and my hydronium. And the thing that they have in common, the H2O, well, that's liquid phase. That's going to go away. And so what I have is this expression would be for my hydroxide, so for my base, and this expression would be for my acid, and that's it. So I can use this then to go any way I need to. Let's see, I am at 25 degrees C, so that means that Kw at 25 degrees C does equal 10 to the negative 14. So I can write Kw then divided by Ka will give me my Kb. Let's go ahead and do that. So 10 to the negative 14 divided by 2.4 times 10 to the negative 5 is going to give me my base. So 10 to the negative 14, let me make sure that's clear. That looks like a 4. Negative 1, 4. There we go. Let's see. So the 10 to the negative 5 is going to come up top. So I'm going to have like 1 over 2.4 times 10 to the negative 14 times 10 to the 5. So 14 minus 5 is 10 to the negative 9. Just a little less button pushing. 10 to the negative 9 divided by 2.4 gives me, let's see, 4.16. Yeah, 4.17. 17 times 10 to the negative 10. Let me just button push that again. 10 to the negative 14 divided by 2.4 times 10 to the negative 5. Yes, of course it equals 0. When you put in the wrong thing, give me a second. Okay, yep, this checks out. So let's go ahead and write this, that our Ka then, or Kb, yep, our Kb is going to equal 4.17 times 10 to the negative 10. I can remind myself that this is only going to have 2 sig figs, so I want to keep that in mind as I go. All right, now let's write out our expression. What am I going to get? I'm going to get C6H5NH2 aqueous plus water liquid is in equilibrium with, let's see, so what have we done? This is my base. That means that this is my weak base. It means this is acting as my weak acid. So that means I'm going to get OH minus aqueous plus, well, I've given a hydrogen to my weak base, so that gives me my C6H5NH3 aqueous. This is now my weak acid. And this OH minus is actually acting as a weak base, even though it is part of our strong bases. Okay, now what about our initial concentrations? We said that you have 0.35, so here's my R, my initial 0.35 molar here. This doesn't count again. My OH minus, so we're going to make the same assumption that I'm going to start with no autoionization of the water, and the concentration is negligible to impact this. We'll come back and check it at the very end. So what's my change? It'll be minus X. This would be plus X, and this would be plus X. So at equilibrium, I have 0.35 minus x, x, and x. So my equilibrium expression then is going to be products OH minus times my conjugate base, or conjugate acid, at 5NH3. God, that's a long compound to write. All right, and then on the bottom here, C6, that's a C. H5 and H2. Cool. Now it's the easy part. Let's just put in our x's. So I'm going to end up with my x over my 0.3535 minus x. Now I want to ask myself, can I ignore my minus x? Check that out. Try to do it without your calculator and come back. All right, so let's check it out. My initial concentration is 0.35. My Kb is 4.17 times 10 to the negative 10. I want to try to do this without my calculator, so I'm going to write this as 3.5 times 10 to the negative 1 times the 10 to the 10 divided by my 4.17. Let's see, so my approximation is that this is going to can be written as 10 to the 9. And let's see, 3.5 divided by 4, so this is ish, 0.9-ish, times 10 to the 9th. So I'm going to end up with like 9 times 10 to the 8th. Ish. I'm rounding in my head, doing an approximation. All right, what does this need to be bigger than? Well, I have 2 sig figs, so is this bigger than 100? And no matter how ishness that is, 10 to 8 is definitely bigger than 100. So yes, we can. So let's go ahead and write out our Kb of 4.17 times 10 to the negative 10 equals x squared divided by 3.5 times 10 to the negative 1. Come over here. I get 4.17 times 10 to the negative 1 times 3.5 times 10, oops, negative 10, 10 to the negative 1. So I don't want to put all those exponents in my calculator because that just gets gnarly. And it's a great place to make mistakes. So I will have 4.17 times 3.5 times 10 to the negative 11. Minus 10 minus 1 is negative 11. And I will put that in my calculator. What do I get? There's that. 10 to the negative 11 times 3.5 to the 1/2. So this gives me 1.2076 times 10 to the negative 5.